Righty.
That sure would have been a hot day.
That doesn't work.
I will always take onions off burger. I don't understand what happened. It doesn't even raw. Everyone raw. Why would I use raw? They're good.
People do that as a prank for caramel apple. Instead of getting apple caramel, they put an onion in
Okay, I know it's pungent, but raw onions like sumac or like lemon.
Yeah.
Don't come on lemon and squeeze.
No, I can guarantee you, if you're like Gordon Ramsay with your onions, you would get cooked. All right. Get cooked more than so I think I got everything set up here.
Raw onions.
All right. So first thing first, today is the last day for everybody to turn in any evidence that you have CISP 430 as a co-requisite or or you have taken that class already. So it can be taking 430 in the same semester like this semester, or you have taken 430 a prior semester. But I need some kind of evidence. Yes.
On my campus, it said that I already got graded for it and already got like 1 out of 1 point for it.
Yeah, if you already got 1 out of 1 in that quote unquote assignment, you're fine.
Okay.
Yeah, that means I have some way to check it already. Particularly for people who have taken 430 already, you probably got a 1 from like last week already. Because I can do a quote unquote indirect prerequisite requirement check for the 360 prerequisite requirement. And as a process of that, I can actually tell whether you have taken 430 or not. So I think you probably got a point from last week already. All right, so you have until tonight, I mean, like sometime today, to turn in a form and then give me the evidence that you turn in a form for those of you who do not have any point, okay, with either one of the checking assignment. So this is one for the Math 372, and this is one for the CISP 430 class. I think most people are done already, but I saw a few people who did not have any score, which means at this point, I do not have any evidence pointing one way or another. So clerical stuff, just want to get it out, make sure that people get those taken care of. So are there any questions from last Wednesday? That was 4 days ago. Do you guys still remember what happened 4 days ago? Yes, go ahead.
How many truth tables of like conjunctions, disjunctions, negations?
Yep.
What inference and bias?
So we were at the point where I gave you something to do over the weekend, and it was about how to use the truth table, use a truth table to show that implication, okay, X implies Y is really the same thing as not X or Y. So that was the last thing that we talked about before today. So let me show you something that I do, okay, before I get into a class. Okay, I'm not going to show the first part, which is going back to the recording, the screen recording of the prior class, because even I cannot remember exactly where I left off in the previous class. So you can probably do the same thing, just kind of go to the recording from the previous class, quickly go through all the stuff, okay, just kind of skip along and just go like, okay, do I remember that? Yep. Okay, now that the video shows this equation, yes, I remember that. So that's a good way to kind of warm up your mind for a class like today. I would say you'll spend 5 minutes, 10 minutes at the most. That should be sufficient to reestablish the context of the content. And let me retrieve. Okay, so this is Joplin. And I think I talked about Joplin, from before too, but I need to, it's not being selected. Okay, let me see if that works. Nope. It's, I'm the key was interpreted or hijacked by another application. So I can always do it here, which is to toggle note list and also to toggle. There's one more thing I need to toggle. I cannot remember what it was because I need to show notebooks. So F11 is not working here. It's hijacked by one of my other windows. I don't know why. It may be because of Zoom hijacking stuff. All right, so that makes it a little bit, there we go. That's what I need. So, and then I also need to look at note list. There we go. So this is for this class, and I am going to make a new note for today. It's going to be 2023-01-23. There we go. So now I can unhide. I can hide the other one. Actually, what I need to do was to go back to the previous one. So this way we have the truth table to fill in. Okay, so you can focus on the right-hand side. I'm going to type on the left-hand side. So according to the definition of implication, false implies false is true. According to implication, the definition of implication, false implies true is also true. The only time the implication itself is false is when you have true implies false. So this is the only time the implication itself is false. And then for the other one, the last one, true implies true is true. All right, so are there any questions at this point about this column that corresponds to X implies Y? There are several ways to look at this. One way is very simple. You just look at that as the definition of implication and just accept that this is just by definition. I'm not going to go any deeper into interpreting why that is the case. So that's one way to look at it, and it's fine. There's nothing wrong with that particular way of looking at things. But then some people look at this and go like, it doesn't make sense to me, okay? Because how can implication itself has a true or false value, okay? If I were you, if I were sitting on that side, I would probably have that question in my mind if this is the first time that I was introduced to implication as an operator. So if you have that question kind of gnawing at you, I can try to answer that question after I finish the truth table. So the last column, the fourth column, is really just evaluating, not X or Y based on the value of each particular row. So in the first row, X is false, not X is going to be true. So since this is an OR, if at least one side of the OR is true, the whole thing is going to be true. So I don't even need to bother with the value of Y. Same thing with the second row, because X is false to begin with, not X is going to be true. So true or whatever is going to be true. Now, okay, so let's digest that a little bit, okay? I just said something, I made a claim. How do you know that claim is actually true? True or whatever is true, that's what I claim. And that's why I don't even bother to look at why. So how do we know that? How do we know true or whatever is true?
Definition of an OR.
Definition of an OR, and if you look at the truth table, if the left-hand side is true, the expression itself is guaranteed true anyway. So that's one way of using the truth table that defines disjunction to basically go like, oh, we just need to know if at least one side is true, the whole thing is going to be true. Okay, but it's important that you question those claims. It's like, okay, when did you mention that? Maybe I did not mention it. Okay, maybe I mentioned something else so that you have the tools to prove it to yourself. So there are these kind of hidden exercises that you can do. Okay, it relies on you, practicing critical thinking, which is like, okay, don't say, if the professor, particularly TAC, said blah, 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 it has to be true, okay? Because I make mistakes. So it's important for you to assess every single one of those statements and go like, okay, how do we know that is the case? Did he show it? or did he show me enough stuff that I can prove it myself? So those are all good questions to ask, when you're taking this class. All right, the third row is the only row when the disjunction returns a false, because in this case, X is true, not X is going to be false. So we know the left-hand side of the disjunction is false, but Y is also false on this particular row. So we end up with false or false, which we also know is false because of the truth table for disjunction. And then for the last row, well, I mean, not X is false, but Y is true. So we end up with true for the entire expression. So is that okay? Are there any questions about the truth table itself? No questions? All right. So if you look at the truth table, the third column is the definition of the implication as an operator. The fourth column, on the other hand, is breaking it up and go like, okay, can we define implication using operators that we are familiar with? And you can see how both of those are the same. So that means, X implies Y really is exactly the same thing as saying not X or Y. So before we proceed to some examples to illustrate implication, do we have any other questions? Huh?
The arrow.
The arrow?
Third column on the left.
You mean this one?
Yeah.
Okay. Let me show you where you can find it. And I do not mean it in a mean way, okay, when I say something like that, because I do want to make sure that everybody know where you can find the material for this class. So that was in Boolean operators. That was the slide that we talked about last time. And it is important that we review the material that we have talked about already. This is where we left off last time. This is implication. And this is the first time that I introduced the operator implication. So that's where it came from. Yes?
How do you type it on the keyboard?
On the keyboard? Okay, so I'm pretty sure I also showed you guys how to find out the LaTeX representation of this. So I'm gonna show you guys again. Right click, show math as tech command. Then you know exactly how it is represented in LaTeX. First, the other way to do it is simply for me to go back to Joplin, because in this case, this is how, okay, this expression X implies Y is made by this portion in Markdown. So between the dollar sign is what we call LaTeX representation, and the LaTeX representation is what turns the / right arrow into a double bar right arrow, which in this class means implication. So I can see there might be some value in reviewing recording from a previous class, because all of these were discussed in the previous class. So you can take notes, okay, in the class. If you say, oh, this seems to be important, take notes. And you can also go back to review the lecture, just in case you missed something important. Are we good so far? All right. So I'm giving you guys the tools, to make sure that you get the content of this class, okay? You may not be able to get 100% of everything that I say in class. You may not be inclined to ask questions in class, but you can go back and review the material and then use my office hour to ask clarification questions. I mean, it's just the hour before this class, unless you have another class right before this one, then we can arrange for a different time. I usually have at least half an hour after class as well. So if you have any questions you need to ask me, you can always ask after class as well. So 1 hour before and about half an hour after class, you can kind of look at those two, segments as my office hours on the same day that you have this class in person. Are we good so far? So that means for some of you, if you don't have a class immediately after this class, you might want to write down in your notes and say that tech is usually available right after class for about half an hour. So this way that resource is available to you. Alrighty, so I said that, if you're one of those people who want to understand the concept intuitively and not just, because it is defined this way. So I'm going to give you an example, and let me go hide the stuff that I don't need anymore. So the sidebar can go away. The note list can also go away. So this way we have, I have more area to talk about things. So I'm going to define a few things. So I'm going to define, let uppercase X here, which has nothing to do with the X and Y in the truth table, be the sentence. Okay, so I'm going to give you a sentence, a statement, which is written in English. So I'm going to say, we'll pick something ridiculous. Okay, the sky is, okay, you guys can choose a very unlikely color that the sky can become.
White.
An overcast day has a white sky.
Well, it's also red. Or purple, maybe.
Purple, okay. Cyan, magenta. Magenta. How's that? Do you know what is the color magenta? Sorry? It can happen? Magenta can happen? How about cyan?
I've seen green blue skies.
How about this? Olive green.
Yeah.
Uh-huh. Yeah, I think that's pretty unlikely. Okay. Okay, so we'll make Y be something that's unrelated to the sky, completely irrelevant. Also something that is unlikely. All cats lose their fur. How about that? So all cats become, just the skin. Okay, there's some, very specific breeds of cat that looks like that. But I'm just saying that, statement Y says, all cats lose their fur. Okay, or become furless. Okay, so now I walk around the classroom, and for each one of you, I collect $5. And for which, so for that money, you're buying a statement from me. Okay, a statement of wisdom. Okay, and the statement of wisdom, if I use mathematical notation, is this. Okay, so let me just say you bought this for $5. Okay. In other words, you gave me $5 and you say, Tech, give me some words of wisdom. And I said, if the sky is olive green, then all cats lose their fur. You go like, that's not what I thought I would buy for $5. Then I go like, well, I got your $5 already. If you want your refund, read the refund policy. All right. Is that okay so far? Does everybody understand the scenario I'm putting you guys into? And no, I do not want your $5. So no need to ask me for my PayPal account. So when do you get a refund? Only if you can show that tag statement is not true. Sounds fair, right? Okay. In other words, if my statement that you bought for $5 turned out to be wrong or false, then I would say, okay, fine, you can have the $5 back. Is that okay? All right. So does everybody kind of understand the scenario? Okay. And I need to go back to Zoom and check a few things because I think it's using the wrong mic, which is probably still okay, but I wanted to use the better mic. Let's see, where do I get that control? Nope. Let me try again. Is there a configuration? It's not from here. I'm not sure where I can get a control, but I think the person who's online says, the audio is good, so I'm going to be okay with that. It's just that if I step away, the mic on my laptop computer is not going to be able to pick up my voice as well. And that thing, which I brought here, can actually pick up my voice really well. All right, so I'm not going to spend too much time to fuss around that. Okay, so now you have 4 scenarios. Okay, so the 4 scenarios is going to be the same as the 4 scenarios that I have already repeated here. So I'm just going to copy and paste down here. Actually, I forgot that this is in the VI key. So it's that to copy. There we go. Except I'm going to use uppercase X and uppercase Y in this case, because X and Y are specifically representing certain things. So here's X, here's Y, and we don't need to deal with that. Okay, so we'll get rid of the last column because we don't need that. Okay. All right. All right, so let's look at this truth table here, which is not that much different from the previous one, but this time we're going to look at it from the context of how do I get my $5 back? Because I need caffeine, I need to go to Starbucks, I need $5, okay, and that $5 seems to be better utilized for coffee. All right, so the first line says, X is false, Y is false, which means you get the day like this, the sky is blue, it is not olive green, and then you go to, you get your cat food out, because we do have a lot of stray cats on this campus. So if you get your cat food out and just put it in the tray, eventually you will see some cats. And you look at those cats and go like, yeah, still pretty furry. So that is now the first row, right? Because X is false, the sky is not olive green, and Y is false as well, because the cat seems pretty furry still. So 0 and 0. So the question is, will you get your money back? Yeah. Can you come back to me and say, Tag, you lied to me, I want my money back? No? Okay. So that means you do not get your money back. So I'll just say no money back. All right, second scenario. X is false, but Y is true. Okay, you look up at the sky, it's blue. And then you walk around the campus, you collect all the stray cats, and every single one of those is furless. You go like, do I get my money back? You do not, right? Because the conditional statement of if the sky is olive green, then all cats lose their fur, does not say anything about what if the sky is not olive green. Okay, maybe nothing is going to happen to the cats. Maybe they all lose their fur. It doesn't matter because my statement did not say anything about what happens when the sky is not olive green. Is that okay? So that means no money back in this case either. The third row is corresponding to you look up at the sky and you're like, that is odd. The sky is olive green. And then you look around, look at all the cats, and they are still pretty furry. That is the one time when you say, Tag, I want my $5 back. Does that make sense? All right. So Tag gives you the $5 back. All right. And then the last scenario is you look up at the sky, it is olive green, and then you walk around the campus, and all the cats have lost their fur. So in that case, make sure you're not going to get your money back, because what I said would happen did happen exactly the way that I predicted, right? So money back on the last one, that one is pretty easy to understand. So no money, money back in this case. So, but when you look at the third column, so instead of saying no money back, technically refunds you for the $5 and no money back. That's basically true and false, because you only get your money back when my statement is proven to be false. So that's one way to look at implication in a more intuitive way. Is that okay, or do we have some more questions about these examples?
What was your statement again? Your statement, what was it?
my statement has two variables. The first one is X, meaning the sky is olive green. The second one is Y, which is all caps in newspaper. And then my statement is X implies Y, which means if the sky is olive green, then all caps newspaper. Because there are several ways to spell out an implication. You can say X implies Y. You can also say if X then Y. You can also say X is a sufficient condition for Y. So all of those are equivalent ways to describe X implies Y. Are we still doing okay so far? All right. Okay, cool. So assuming if you guys have any questions, don't hesitate to ask. But assuming we're okay here, we're going to go back to the notes, which I hope all of you had a chance to pre-read before the class. Ooh, secret deal. I'm sorry about the notification. I need to kill that browser before it notifies me about even more deals. All right, so in the notes here, there is an actual different example. A blue cat is sick implies tomorrow is doomsday. So you can read this one. It's just as absurd as a sentence, but it illustrates exactly the same point. Okay, so I would advise you to read all the notes. Okay, because I wrote these notes for a reason. Reason number one is note to self, so that I remember what I need to teach. But the second purpose of the note is for you guys to read, okay? So the last one is equivalence, which is useful, but it's really simple, easy to define, because equivalence uses this double-sided, double bar, arrow thing. X and Y are equivalent means X implies Y and Y implies X. And if you work out the truth table, because now we already know the truth table for implication. So if you work out the truth table based on this particular definition, then you end up with this truth table here. The only time the is equivalent with is going to be true is when X and Y are the same. So false, if and only if false is true. Yep.
This is essentially a double equivalent.
Sort of. So if you want to look at this as double equal to, then you also have to put a type limitation or constraint to it, because this only applies to when the left-hand side and the right-hand side are Boolean. So if the left-hand side and the right-hand side are both Boolean, then double equal to in C and C++ can be considered the same thing as equivalence here. Logically speaking, right? Which is not going to work out all the time, because in C and also C++, any value other than 0 is considered true, right? So that means, if you have X being true, but it's not actually a Boolean, and Y is also true, but it's not a Boolean, and then you use a double equal to, you can fail the double equal to, which means the double equal, is going to return false, and yet, if you look at X and Y as Boolean values, they are both true. Does everybody know what I just said? What I was just talking about. That problem does not exist with Java, because Java has no automatic type conversion between anything and Boolean. If you try to use double ampersand and one side is an integer, the other side is also an integer, Java is going to complain and say, you cannot do this. It doesn't make sense to have a logical and between two integer values. Okay, because it doesn't automatically convert the type of integer into Boolean. But C++ does that conversion automatically. So if the C++ compiler sees the double bar operator, which is OR, and one side there's a float, on the other side there's an integer, the C compiler goes like, yeah, based on the operator, I know how I'm supposed to look at the left-hand side and the right-hand side. And then it would basically say, if it's a 0, it's false. If it's non-zero, it is true. So the C++ compiler automatically convert the value based on the type. And that does not happen automatically with Java. Is that okay? I mean, all right, okay, cool. Because those are really important concepts to understand, not from the perspective of this class as CISP440, but those are very fundamental concepts of programming languages and also the differences between programming languages, which also means by the time you graduate, by the time you get a job, most likely than not, you're not going to be programming in a programming language that you have been taught. And don't tell this to your C++ professor, obviously, right? But it's very likely. I mean, there are lots of programming languages like Rust, okay, is one, Go is another one. I mean, there's a bazillion programming languages out there. We only teach C++ and Java. And your four-year university is likely to be only teaching C++ also within their main curriculum. You might learn Python on the side, JavaScript on the side, and stuff like that. But by the time you graduate, there'll be new programming languages introduced. So you will need to understand these concepts: automated, type conversion, strong type checking, weak type checking, and so on and so forth, in order to learn all of those new programming languages by yourself. All right. So do we have any questions about this particular module before we move on? When I say module, it is my module, which is just something that I write and not in the sense of Canvas module. We good? All right. So if we are good there, I'm going to close this tab and then we're going to move on. So the way I teach is really just moving on to the next available concept, which in this case is basic set theory. I won't even call that theory, okay? It's more like just notations. What notations do we use when we use the concept of sets? So we'll go ahead and start with a set and its elements. So basically, you can look at a set as a container. That's basically all it is, okay? It's just a container of stuff. So the best analogy I can come up with is a folder, okay? If you think about a folder on your computer, on your phone, okay, it is a container. So the other important concept, when we have the concept of a container, is things that you can put in a container, right? You can look at a thing and you ask, is this thing in a container or not? Okay, if you can answer that question, hey, you understand the most important part of what is a set and what is an element. So the set is a folder, and then whatever can be put into a folder is an element. Are we good so far with those terms? Okay, so that's basically what a few first paragraphs are talking about. So elements within a set, okay, or files within a folder, there's no intrinsic ordering. So it's kind of like, when you have files in a folder, the way the files are listed, you can list it by file name. You can list it by the last time you modified the file. There are many other ways for you to kind of sort the items, but there's no intrinsic ordering within those items. So the only thing you can check is really, is this file in that folder? Is this element in that particular set? That's pretty much the only question you can ask. Are we good so far? Right. So that covers everything to this paragraph here, which says elements in a set are not ordered. There is no intrinsic or inherent ordering of elements in a set. And then we move on to the last important concept is all elements in the set must be unique. So you can kind of ask yourself, with any known operating system, Linux, Mac OS, Windows, and so on, can you have two files of exactly the file name in a folder? So I'm so glad you guys are all turning your head, because if I were to ask this question in a different class, people would not. Because by default, Windows hide the extension of files. So that means if you have xyz.abc and then have xyz.xyz, it will show both only as xyz, but with a different icon based on the extension. But since you already know that there's an extension to a file, and if the extension is different, the file name is still considered different, right? So it's the same idea, okay? In a set, you can only have up to one element. Okay, you cannot have two elements of exactly the same value. Is that okay? The other way to say this is every element within a set has to be unique within the set. We good so far? All right. So, the concept of a set is not that complicated. And if you, in certain cases, not all cases, in very few cases, sometimes you have a set that has a very small number of elements, then you can go ahead and enumerate and list all of those values within the set. So that is using this notation. You always use a brace, a pair of braces to enclose the items. And then within the braces, we use a comma separated list of the actual items within the set. Are we good with that notation? So we don't use brackets, we don't use parentheses, we use braces. Is that okay? All right. So let's say that T, uppercase T as a set is defined exactly like this. So that means 12 is an element, 5 is an element, 2.2 is an element, 7 is an element, -1 is an element, and then 10 is also an element, and that's it. Everything else are not elements within this particular set. So in that case, we can now define the first operator about set. Okay, between elements and a set. It is called the element of operator. This operator returns a value that is either true or false. And in this example, if T is defined exactly like this, then 2.2 is an element of T is true. On the other hand, 23 is an element of T is false. In other words, this symbol here that looks like a funny looking uppercase E is an operator. It is an operator is asking, is the left-hand side an element of, no, I take it back, I got the direction wrong. Is the left-hand side an element of the right-hand side? So the right-hand side has to be a set. The left-hand side can be anything. So I'm going to pause here to make sure that the notations are all clear. There are no questions about the notations themselves. Are we good so far? All right, okay. So food for thought, how would you implement the concept of a set in C or C++? Do you know ahead, if you know ahead of time, a set is only to contain integer values, how would you implement a set? How do you check whether a value is an element of a set or membership of a set? How do you place elements into a set? So there's nothing to turn in. This is really just a thought experiment that I want you guys to kind of spend some time on. Because the concept of a set, even though it is a little bit abstract, it is not so abstract that we don't really use it in programming. So the concept of whether something is in a set or not is actually utilized in even super low level programming in computer science. I probably don't need to give you the specific example, but there are certain system calls that utilize the concept of a set to ask the question of, okay, you're handling a bunch of files. Which file has a read operation pending, for something that you can read, and which file is ready for you to write content to. So that particular system call utilizes the concept of a set, but it uses a very primitive way of implementing the concept of a set, which is just using one bit of each bit of an integer is representing a particular file handle, which is just an integer. And then it uses bitwise operation like and or not, bitwise and, bitwise or, bitwise not, to figure out whether a file descriptor FD is in the set or not. So I'm only going to go that far, because it's not relevant to the content of this class. But what is relevant to the content of this class is set as a concept is not only for abstract algorithm description, which we'll do in this semester, in this class, but it's also actually used in general purpose programming. So that's all I'm going to talk about, with that section 2.1. So now we'll move on to section 3, which is asking if I have set X over here and we have set Y over here, how can you tell whether X and Y are the same? So we'll take a look at this. A set can be compared to another set to see if they are the same. At this point, okay, because we're going to revisit this later, we lack the precise mathematical notation for this kind of discussion. Okay, bad grammar here. But we can still utilize English for the most part. Let's say we're interested in whether set S or T and T are the same. The two sets are considered the same if every element in S is in T and every element in T is also in S. So that's our kind of loose, definition of equivalency between two sets for now. So does that make sense to you? If I have, two thumb drives, okay, and I ask you, are these two, is the content of these two thumb drives exactly the same? So you check the first thumb drive and you say, okay, I find this file on this thumb drive. You check the second thumb drive. Do you have the same file with the same content? Yes. Okay. What about the second file over here? Check. Yep. Third file, check, and so on. But you cannot just check everything from this thumb drive against this thumb drive, because the second thumb drive may contain some additional files. So in which case, you cannot say the two thumb drives have exactly the same content. So you have to make sure whatever is in the first one is also in the second one, but whatever is in the second one is also in the first one. So that reverse direction is really important. All right, are we good so far with the equivalence of sets? Yes.
They don't have to be in the same order, they just have to have the same stuff.
There's no intrinsic ordering. So you just need a way to look at every single one. So this is where things can get a little odd, because we are all used to programming in a sequential way, which means if I give you a bag, which is a container, there's always an order of what you retrieve first from the bag, what is the second thing that you retrieve, even though I just said, okay, for everything in the bag, do this, okay? But there's always an intrinsic order of which one you process first. So I'm only saying that ordering is not important. Is that okay? All right. So the third, section 4 talks about, a set as an element of another set. So this sounds like a recursive-ish kind of definition, but it's not. It sounds like it's really abstract. It's also not, because all I need to do is to ask, can I have a folder inside another folder? If I make a folder for all the homework assignments for CISP440, can I make a subfolder for the first assignment, another subfolder for assignment 2? And then within assignment 1, can I create even more subfolders if I need to organize things a little bit better? The answer is yes. So it's the same thing with the concept of using sets, because you can have a set inside a set. Now, I know most of you are thinking, some of you, because you have heard about that term, so is that what subset is about? The answer is no, okay? That has to do with, that confusion has to do with what we understand about folders and subfolders. When you create a folder inside a folder, the folder that's created is called a subfolder, right? But the concept of a subset of a set is a little bit different. We'll talk about that later, okay? Just do not equate a subfolder to a folder is the same thing as a subset to a set, okay? All right. So recall that to qualify as a potential element, a value must be comparable to other values to determine whether they are the same or not. In the previous section, we just established that a set can be compared to another set to see if they are the same. So the same means, if I can find it here, I can find it on the other side and vice versa. In general, given two values, X and Y, given that knowing that X is a set already, this is how we can determine whether X equals Y is true or not. If Y is not even a set, then we have a type mismatch, then X equals Y is going to be false. If Y is also a set, then we use what we talked about in section 3 to determine whether the equivalency is true or not. Now that we can compare a set with anything for equality, it is not surprising that a set can be an element of another set. For example, X is defined to be a set. Well, okay, so let me ask you, if I want to know how many elements are in X, what would be the answer? 3. 3 is correct. Okay, good job. Okay, because from the folder perspective, X is a folder. It has a file A, it has another file B, and then it has a subfolder. And within that subfolder, we have the files 1, 2, and 3. So if you are to just look into X as a folder, there are only 3 items that you can see. So 3 is the correct answer. Very good. And we can also look at this particular expression here. So this is an expression. It can be true, it can be false, because this expression here is really just asking the set that contains 1, 2, and 3 as its only elements. Is that set by itself an element of X as X is defined earlier? And then the answer is yes, it is. Is that okay? All right. So let me just push this in here so I don't trip over my own bag. All right, section 5 is a notation thing. In fact, this entire module is more or less, just talking about notations. So there are some times, most of the time, we cannot enumerate, we cannot list everything inside a set because the number of elements is infinite. There's no way for me to enumerate every single element in a set. So now the question is, in those cases, what do we do? So the first thing is, we need some symbols to begin with, like this symbol here that looks like a Z, but not exactly like a normal Z. And I can show you how this is done. Remember, show math as, and then tag command. So this is math BB, and then in braces, Z. So if that is what you want to do in your notation, in your notes and stuff like that, that's what you need to type. So this is representing the set of all integers, okay? So because of the way it is defined, we already know what it has, okay? Or what elements do we have contained inside that particular set. Likewise, this funny looking R refers to the set of all real numbers. Do we have any questions regarding what is the differences between the set of integers versus the set of all real numbers? Do we have any questions? No. Okay, all right. So now we move on and we talk about the set of all even integers is also a set of infinite elements, or there's an infinite number of elements in the set of even integers. But how do we express it? How do you say, okay, look at this set here. This is the set of all the even numbers, even integers. How do we express it? So it is a notation kind of question. So the most intuitive answer for most people is to express it kind of like this, okay? E equals to ... okay, ellipses, -4, -2, 0, 2, 4, and so on. But that's ambiguous, right? Who knows what's before -4? And who knows what's after 4? For all I know, it can be -8 right before the -4, and it's an 8 after 4, right? So we're only looking at, positive and negative exponents of 2, which doesn't make sense because 0 should have been the 1 in that case. But the point is, this is ambiguous, okay? It doesn't really clearly state that this is the set of all even numbers. So that means, we need something that's more definitive. We need something that is more precisely describing the membership of a set. So you might notice that in this class, I might repeatedly use the phrase or the word or the adjective to be more precise, and the adjective is precise itself. So why do you think it is important for me to emphasize precision in terms of the expressions, in terms of what I'm describing and what I'm explaining? What is the importance of precision? Yep.
So there's no ambiguity, but why is ambiguity not such a good thing? I mean, if this were a poetry class, ambiguity may be a good thing to have,
Coding,
right?
coding is hard to be ambiguous.
Coding, if it is ambiguous, if the description of what needs to be done is ambiguous, then the computer doesn't know how to do it. Because there are multiple ways to interpret the description, and then the computer can only choose one, right? So all computer programming languages are precise to begin with. There are no ambiguous programming languages. There's ambiguous understanding of a programming language about the syntax, about what it does, and so on, but the programming language itself cannot be ambiguous. Does that make sense to you? Okay. So what we are doing here, okay, this class is not exactly a programming class. This is more of a math class. So in mathematics, it is just as important to focus on precision, because we need to know exactly what we are talking about. So we'll see some other examples of precision, why that is important. So the following notation can be used as a precise method to describe a set of even numbers. So this is the first one, okay? There's an alternative later on. So the way we read this sentence here is to say E is defined to be a set, okay? How do we know it's a set? We see braces, okay? One to begin here and one to end over here. So it is a set. So what about this set here? So this set consists of elements X, okay? So X is a variable. So X is a variable in this case to basically say, in order to describe each and every element in this particular set, then each and every element X has to pass the following test. Is that okay? So X on the left-hand side of the bar is merely indicating which variable is describing each element in the set. The right-hand side of the bar describes a test and basically say every element in the set has to pass this test. And for every value that passes this test, it has to be an element of this particular set. Is that okay? So the left-hand side of the bar is kind of like the declaration of a variable, int X, that sort of thing. And then the right-hand side of the bar is a test to see if a value should be in the set or not. Are we good with that? Yes. Okay. All right, so let's check out in this case what we are describing here. All right, so without going back to the earlier parts of my discussion today, what does that mean? E funny looking E Z, X funny looking Z. What does that mean? X is an element of Z. Is X an element of Z? Or in this case, I want to confirm that. Because this entire expression, okay, so let me point out from where to where. So starting from here, all the way ending here, is a conjunction. So this conjunction has to be true for every value that is an element in E. All right. Now, I'm not saying anyone in this class is having that question in that person's mind, but if anyone is asking, what is this, inverted V symbol? Well, my suggestion is to review the notes a little bit more and possibly rewatch the video, because it is super important to get all the notations and all the definitions familiarized before the next class. Because we keep stacking things up, okay? So it's like playing Jenga. You gotta build a solid foundation, in order to build more concepts on top of the older concepts. So this is conjunction, which is and. So in order for the conjunction to be true, we need both sides of the conjunction to be true. So that means we need this to be true, which means X has to be an integer to begin with, because this says X is an element of the set of all integers, which means X is an integer. And then the other side uses the mod operator. It says X mod 2 has to equal to 0.
So that's coming from CISP 360, 400-ish, type of discussion, maybe even 300, because I talk about that concept in 300. So when you look at the remainder of x divided by 2, it would be 0 if and only if x is an even number. So this is one way to confirm that x is an even number. Are we good so far? Now, there's always the argument of whether if I use this already, do I really need this? In other words, if I already says, x mod 2 equals to 0, do I still need to say that x is an element of the set of all integers? That's kind of questionable, but it doesn't hurt to include x is an element of the set of all integers. Are we good so far? Good. All right. So this notation, okay, so, I think I just said that earlier. Something x is an element of set E if and only if. Now, this is important, okay, because, I'm surprised that nobody called out and say, Tag, you never said anything is if and only if. Well, we sort of talk about the operator, but I didn't call it if and only if. Okay, so now you have to play detective. Which operator that Tag had talked about up to this point in the semester is the same thing as if and only if? Not quite. Well, I mean, it can be defined using and as one of the components, but it has its own name. We just talked about it in the slide in the module that I closed already. Equivalence, very good. Okay, so equivalence is the same thing as if and only if. The double bar, double arrow is also known as if and only if. Okay, so let me put it on the slide for today. So let me. Today is the 23rd. There we go. Okay, so I can now put it here. Okay, so this is left, right arrow is also known as if and only if, or abbreviated to IFF. Is that okay? So every time you see if and only if, it really is saying the same thing as is equivalent to, or you can also abbreviate it to IFF. And that really brings up an interesting question about programming. Well, I thought this class is not about programming. Well, it's not, but I have to kind of show you, the context in terms of programming. Okay, so I will say, if x is less than y, this is in C code, so you can pretend this is actually C code. I'll even use braces, okay, to make it very clear. This is the only thing we do. So we only print f, x is less than y. Okay, I'll spell it out. X is less than y. There we go. Semicolon. Okay. So if you just look at the statement here, if x is less than y, print x is less than y. Okay, sounds pretty simple, right? So let me ask you this question. What if x is 2 and y is 1? Then what is the behavior you should expect from this conditional statement?
It's false, so it passes it by.
It skips over, right? It skips over the printf statement. That is your understanding. But that's not what if means. Because if you think about this statement as a conditional statement, okay, and we want it to be true, right? So once again, we have to go back to the truth table of implication or implies or if then, right? There are 3 rows in which it is true. The one that you know is if x is indeed less than y, we should print x is less than y. That's corresponding to when the left-hand side and the right-hand side of implication are both true. Okay, that certainly is one row, when the expression itself is supposed to be true. But we have 2 more rows in which the implication is true. And they have to do with what happens when the condition is false. If the condition of an implication is false, it doesn't matter what the right-hand side is. So if this is truly, if, okay, that's a really awful way to say it. Let me rephrase it. In the case that IF as a keyword truly means implication, this code is not telling us what we should do when X is not less than Y. Put it that way. Is that clear or not? So what is the solution? What is the proper way to fix this problem? Because the way a mathematician or a logician understands if, which is just a plain right arrow from your perspective, is basically saying, if this is, the statement, then it doesn't tell us what to do when X is not less than Y. Maybe we'll print, maybe we won't print. Okay, both are acceptable because in the truth table, okay, if the left-hand side, which is X is less than Y, which is X is less than Y, is false, then it doesn't matter what the right-hand side is. Okay, it can be true, it can be false, it doesn't matter. So what is the proper way to fix this little problem here? But what is the problem to begin with?
We have a situation where we don't know what to do.
Right, but how did that problem come up?
X is not less than 1.
It has to do with, from the earliest day when computer scientists invented programming languages, they were not being precise. They should have named the keyword IFF. They should have said, if and only if X is less than Y, printf. That is what they should have done. So by missing this one F here, it is now, there's a discrepancy between what we understand in terms of programming of what this is supposed to do versus, from a logical perspective, what it is supposed to do. I'm not sure how much it is making sense to you. If it is making sense to you, that's all good. If it's not making too much sense to you, it's probably okay. But I would point it out because, to me, this is like something that sticks out. It's like, ugh, ew. Yep.
I was gonna say, since that is technically the if and only if statement, is there like a keyword that would go, like that would correspond to logical if?
There's no logical if in C whatsoever.
Okay.
Yep. So for those of you who are really after today, you go like, oh, okay, we have to do things in a much more precise way. You can always do this in the C++ program. So basically, you're using a macro definition of IFF, and you're just saying from here on, IFF is really the same thing as IF, and then the C compiler would not know the difference. But from your perspective, as a logician / programmer, you will feel like, okay, that feels a lot better because now I know there's congruency between the logic of if FIFF and the behavior of the program using IFF. And of course, if you do this to all your homework assignments, then you turn it into CISP440. For those of you who are turning in 430 homework assignments, the professor will probably just kind of comment and go like, why do you do this? It's not wrong per se. It's just like most people don't do it. Why would you do something like this? You can say, yeah, but tax said, something blah, blah, blah. And then they will all understand it. Go like, yeah, okay, fine. We kind of expect that. Okay. Okay, so, and you might think, all of this stuff here is really irrelevant, because who would go to that length to kind of go like, yeah, but programming means, that means the keyword is wrong. Not too many people would. Is it practical? Is it pragmatic? I would say no, but being able to find that it is a incorrect use of the word if in the context of a conditional statement, I think it is still important to be able to say, yeah, that's not entirely right. Okay.
All right, so we're moving on. Right, so we are now generalizing.
So in general, blah, blah, blah. So in general, if we consider P of X as a general predicate P on X as a function that returns true or false based on X, then blah, blah, blah. Okay, so let me first start with what is P of X. So P of X is simply, from your perspective, it is a function that returns a Boolean value. That's all it is. Okay, it's a function that returns a Boolean true false value, and it uses X as a parameter. That's what a predicate is. It's just a fancy name. So the purpose of this is I want to generalize, okay? I want to generalize the notation. So basically all I'm saying is this notation and this notation mean exactly the same thing. That's all I want to say. So what about those two notations? Well, in this notation, this is what we saw earlier, okay? Except in this case, P of X is kind of really spelled out. And except in this case, P of X is just say, okay, give me some predicate, a function that returns true or false, based on the value of X. We can do it this way to say that E is a set. For each element X in set E, P of X needs to be true. That's basically what it says. But that's really saying the same thing as X is an element of E if and only if P of X is true. They mean exactly the same thing. Both of these are really just specifying membership of E. Who is a member? Who's not a member? How do we decide? So do we have any questions about the two forms of defining membership of a set where potentially you can have an infinite number of elements? So there's no way you can actually just enumerate or list all the elements. No questions? All right. So let us generalize this to the following example. X equals to E such that P of E, in this notation, P of E is a predicate on E. It is some kind of Boolean expression parameterized by E, which is what I said earlier. Given that P is a predicate, this notation says the following: P of X, if and only if X is an element of uppercase X, because in this case, X is the name of the set itself, uppercase X. This means that any value that makes P true must be an element of set X. Any value that makes P false must not be an element of set X. So this operator here, if and only if, is really important. Because if I only use one direction, then it's not the right definition. It has to be a bi-direction thing here. Are we okay so far? Do you guys want me to kind of stay on this for a little bit more, or should we proceed to the next concept? I think I'll just give you one more, okay? Just look at this particular expression here. So in this case, if X is indeed an element of E, then I know for sure that P of X is going to be true. On the other hand, if I find a value that is not in E, then I know for sure that P of that particular value is false. And then to look at it in a backward way, if I just test, okay, in P of X turns out to be true, then I know that value is an element of E. If I test X so that P of X is false, then I know X cannot be an element of E. So those four cases are important because those are the four possible scenarios. Are we good so far? Can someone summarize what I just said? What four cases are we talking about? The four cases has to do with confirming the left-hand side is true, confirming the left-hand side is, okay, I cannot remember what I said. Confirming the left-hand side is true, confirming the left-hand side is false, confirming the right-hand side is true, confirming the right-hand side is false. Those are the four possible cases, and each one will point to the other side and say, since I know something about this side, I know that side is blah, blah, blah. So those are the four cases that you need to think about. All right. So we are now moving on to number 6, which is
an empty set, a set that has no elements. So once again, it sounds like an abstract concept, but it's not, okay? Because you guys know that you can create a folder and not to put anything in that folder. It's just an empty folder. There's nothing in it. Is that okay? An empty set is basically essentially an empty folder. There's nothing in it.
but the empty set itself exists. Okay, just like an empty folder can live in your file system. Okay, it may not have a really useful, there may not be a usefulness to it, but it can exist in your file system. All right, so any questions before we move on?
Because the rest of this discussion here also hinges on the operators that we have talked about so far. I'm not gonna take row today, so for those of you who are thinking about, when is it gonna take row? I'm not gonna take row today. It's a good sign that no one just kind of walks out of the classroom right now. It's like, oh, if you're not taking row, I'm out of here. That would not be a good sign.
Okay, so now we are moving on to set operators. So the first one is the operator called intersection. So this is the intersection between set A and set B.
All right, so there are several ways to describe an intersection between two sets. One way to describe it is to verbally describe it and to say that the element of the intersection between two sets has to exist in both of those sets. That would be an English description of what is the intersection between the set A and set B in this example.
But as a verbal description, it is not precise. It lacks precision. So I'm using the definition notation that we used earlier, both here and also here. These two are equivalent.
But we'll look at one at a time.
We'll just look at the one where the mouse pointer is pointing to. So that one says, if you look at the intersection between A and B, we know it is a set because of the use of the braces. And then for each element in the intersection, it has to meet all of these requirements. It is a conjunction. So that means E in A has to be true. It also means E in B also has to be true. Is that okay? So all it is saying is every element in the intersection between set A and set B, the element has to be an element of A. It also has to be an element of B. Are we okay so far? Okay. So the next one is the union between A and B. So the result of union as an operator is also a set because you can see how this equality is equaling a set notation. And you can also see how these two definitions are really close, except this one is using conjunction, the other one is using disjunction. So that means in the case of a union,
an element is in the union of A and B if and only if the element can be found in A or the element can be found in B. So let me ask you this question. What if both A and B have that particular element? Would that element still be in the union? The answer is yes. Okay, so when I say or, it does not mean either or. It simply is or. Question?
Wouldn't be listed twice, it will only be listed once, right?
It will only be listed once because of the earlier rule about how elements in a set has to be, they have to be unique.
So the union and the intersection.
Correct.
as well.
Yep. All right, so I can give you some examples or some exercises just to see if we fully understand the concepts. And that's what the Joplin is really good for, is for me to kind of create examples on the fly so that you guys can go like, okay, let's work this out. All right, so we'll go ahead and work with the first one, which is A, B, C. Oh, I forgot to use the $sign. So this way I can use the actual math symbol. The intersection symbol is called cap. So cap 1, 2, 3. All right, so what is this going to look like? What should I put inside the curly braces? Oops. You know, I forgot to put curly braces, and that has to do with in LaTeX, curly braces are special. So you have to put a backslash between before the curly braces in order to escape it so that it actually shows up as a curly brace. There we go. So that was much better. Okay, so we're looking at the intersection of A, B, C as a set. 1, 2, 3, that's another set. So what is the answer of that question? The empty set. Yep, this is the answer. Okay, very good. So we'll take a look at another example. Okay, so we have A2, A1C. And then on the other side, we have 1B3. So what would be the answer in this case? Just 1 itself. Yep, because 1 is the only common element between the two sets. So that's another way to describe the intersection is it is the set of common elements between two sets. So that's one way to look at intersection. And what about this? A, B, C as one set intersecting with the empty set. What would that be? It would be the empty set. Because the empty set has nothing in it. So if I were to find something that is in both of these sets, there'll be nothing. Because the empty set has nothing in it. Very good. All right. So I can repeat these and turn those into union. Sure, I can do it like this. And let's see, let me see if I can do this. Yep, cool. The VI commands actually work in this editor. So I was able to convert all the intersection operators to union operators here using one simple command. That's kind of cool. All right, so getting to the actual question here. So what is the union between these two? Yep, A, B, C, 1, 2, 3. Very good. What about this one? A, B, C, 1, 1, 3, 1, 3, not 1, 1, 3. There's only because 1 cannot repeat itself. Okay. And what about this one here? Just A, B, C. Yep, that is correct. Oops. Very good. Well, you guys are getting all of this stuff here. So let me throw some wrenches into this whole thing and see whether we are okay with those two. So this time we have A, B, okay. And we are unioning with another set that has as its own element, AB as a set. Yep. Yep, that is correct. So we have A, B, and then the set containing AB in it. Very good. All right, well, then we can test another one, which is how about this one? This is not the answer. I'm just putting in the braces. So what is the intersection of two sets? Each one contains the empty set as an element.
Inside
An empty set inside the set.
Yeah.
Cannot be an empty set inside the empty set because an empty set cannot have an empty set. Otherwise, it would be empty.
So the answer, okay, let me put in the answer first and then I'll see if there are any questions about that. This is the correct answer. So I'll be good.
Actually, third bullet up, since you brought up like the ABC union empty set.
Uh-huh.
After the C in the answer, can you technically put a comma and say empty set as part of like the answer? So you know how we had.
You mean this one?
Yeah, we put like a comma and then empty set after, or,
You mean here?
yeah,
No,
you can't.
you cannot, because this set here has nothing in it.
Yeah.
So if you're asking about what values is in at least one of these two sets, you can only say A, B, or C. Empty set as a value did not exist on the left-hand side, it did not exist on the right-hand side either.
I see.
All right, so let me use another example to kind of help clarify what you were asking. So if I did something like this, then the empty set would also be an element inside the union. Yep. All right, very cool. Let me look at the time. We are over time already. So this is where we are leaving off for now. So what I need you guys to do is to finish reading this entire module and also to get into quantification or quantifiers. So before Wednesday, you need to read everything up to here, which is your basic set theory, but it will be very helpful to also get into quantifiers. All right, very good. So we are almost ready for the first homework assignment. On Wednesday, I'll give you the first homework assignment on set locations. All righty.
I just want to know, do you have videos from previous semesters? I tried to look through the some prompts YouTube channel.